This is section 2.6, part 1 of rational functions. We are going to look at rational functions in the sense of this section. We are going to specifically talk about parts of the rational function, the domain of rational functions, the range, asymptotes, things like that. So let's just kind of get into this. So we're going to analyze them, domain and asymptotes. Okay, so let's first define what a rational function is. Sorry about that. A rational function is the quotient of two polynomial functions. So, in other words, we have a polynomial on top, we have a polynomial on bottom. Remember, a polynomial is anything with degrees, like, with 1, 2, 3, 4, 5, 6. No fractional powers, no negative exponents, okay, just regular integer exponents that are positive. So, we have a function on top, a function on bottom. Now, the important thing to note is that the bottom of any quotient can never be equal to 0. So in the case here, b of x cannot be equal to 0. So the domain of a rational function will always be all real numbers except for where the bottom is equal to 0. Okay, so that's really important because that's going to help us define not only what our domain is, but help us find asymptotes. And this is stuff that you did learn in Algebra 2, so hopefully this will not be a whole lot of new material. There will be a couple things that we will go over that will be important at some point here. So, all right, so moving on. So looking at a rational function, we have our parent function, which I'm going to move this so we can see it a little bit better. So our parent function is 1 over x, and this is what it looks like. So 1 over x, you see there's a couple of things going on. We have two zones on our graph, and you should notice that we have two things that the graph never touches. We have this, the y-axis is where it never touches, and then the x-axis is where it never touches. Okay, so going across here. So those are called asymptotes. The vertical line is the vertical asymptote. The horizontal line is going to be the horizontal asymptote. And that's all going to be derived based on what type of function we have. And there's going to be a couple of different ways that we can look at this. So when we see a parent graph, there's a couple things that we should notice. One is that a parent graph is technically looking like this. So what we have here is the same as any other function. Our h will always be our horizontal left and right shift, and our k will always be our vertical shift, our up and down shift. Okay? Now, not all rational functions are given in this form, and you won't see them very often in this form, but it is important for you to kind of get an idea of how we could shift a normal function if needed. But essentially, the bottom is going to be the most important part because that's going to determine where our vertical asymptotes are. Our k technically is a horizontal asymptote, but we're going to figure out how to find horizontal asymptotes in a different way. So this is what the parent function looks like. This is what almost all rational functions are going to look like in some shape or form. Okay, so let's talk about vertical asymptotes. Vertical asymptotes, now this is going to be a little bit different than what you learned in Algebra 2. We want to frame it in terms of calculus, in terms of limits. So again, I'm going to make this a little bit smaller if I can, so that way I can manipulate it a little bit more. Okay, so here we have our vertical and horizontal asymptotes. So with the vertical asymptote, it's much more clear than the horizontal asymptote. If you see, it says the line x equals c. That's a vertical line. It's a vertical asymptote of the graph if the limit as you approach a value, in other words, as I approach this value, if it goes to positive infinity or if it goes to negative infinity, that is considered a vertical asymptote. So you see here, our limit, that limit just means as x approaches something, what does our f of x do? Just like the end behavior. The only difference is now is our x is approaching a number. So we're going to call this, in this case, it's negative 2. So in this case, we would say the limit as x approaches 2, and then this little sign up here just means from which direction. So this is from the negative side. So we're approaching from this side, and then what is our f of x doing? It's going up to positive infinity. And then if you look at the same thing, the limit as x approaches 2 from the positive side, that would be here, you can see that our f of x is going to positive infinity. So because it's going to positive or negative infinity, that is what we call an asymptote. The only way that we could be going to positive infinity or negative infinity is if we have some type of asymptote like this, okay? So that's really important. As you approach one single value, if it's going straight up to infinity or straight down, that's a vertical asymptote. Now, how do we find vertical asymptotes? Really simple. It's where the bottom is equal to 0. Vertical asymptote is where a function is undefined. Now, that's not always true. We're going to get into that in a part 2, but undefined. So that means denominator equals 0. We have to know that. That is so important. Don't try and memorize, oh, it's where the bottom equals 0. Understand vertical asymptotes are where a function is undefined. So if it's where it's undefined, then think about where a function is undefined when the fraction is 0 on the denominator. Okay, so that's vertical asymptote. Horizontal asymptote is a little bit different and a little bit more tricky. So what I want to do is we're going to give some rules here. So first of all, the horizontal asymptote in terms of calculus, it is as your x goes to infinity, what does your f of x go to? So the end behaviors we did before, we talked a lot about whether it goes to infinity or negative infinity. Well, if that's the case, there is no horizontal asymptote. But here you can see as I go further and further to the left, you can see that my line is approaching this line right here. This line of, this line of 6. So that would be where our horizontal asymptote is, because as you go to negative infinity or to positive infinity, you'll see that our line is getting really, really, really close to x or to y equals 6. So therefore, our horizontal asymptote here would be y equals 6. Now, it's not always that easy to look at a graph and see that. So let's talk about a few rules that we need to know. And again, you learned these a little bit in Algebra 2, but we're going to go over them again. Everything is dependent on the degree of your function. So we're going to say we have 3 rules. If the degree of top is less than the degree of the bottom, okay, then our horizontal asymptote, we're going to call that HA, is y equals 0. Okay, second property, okay, degree of the top is greater than degree of the bottom. We have no horizontal asymptote, and actually you're going to end up getting a slant asymptote, and we're going to talk about that in part 2. Okay, so degree of the top is greater than the degree of the bottom. We will have no horizontal asymptote. And if the degree of the top is equal to the degree of the bottom, then the horizontal asymptote will be the ratio of the leading coefficients. We'll call that leading coefficients. Okay, so if you look at this down here, this is a perfect example. So we have 6x squared over x squared plus 2. The degree is 2, the degree is 2. They're the same. So the ratio, the number in front of this x here is 1. So the ratio of the leading coefficients is just y equals 6 over 1, which equals 6. And you see that should match right there, and it does. Okay, so that's the case where you have a different horizontal asymptote than just 0. It's if the degrees are the same, and then you have a ratio between top and bottom. All right, so let's look at a couple of examples here. All right, so find the vertical and horizontal asymptotes for x plus 4 and x minus 3. So if you look at this, the vertical asymptotes is going to be where the bottom is equal to 0. What makes it undefined? Well, x equals 3. Notice I put x equals. That's important. You need to make sure that you're writing x equals or y equals, depending on which one you're trying to find. For our horizontal asymptote, we look at the degree. So the degree here is 1. The degree here is 1. They're the same. What are the leading coefficients? 1 over 1. So real easy. The horizontal asymptote is y equals 1. And that's it. And if you look at the graph, you can kind of see that. If we were to draw a vertical line, we would see that it's at x equals 3. And if we were to draw a horizontal line, you'd see that it's at y equals 1. Okay, as simple as that. That you don't need to make it any more complicated than that. Most important thing is being able to find the asymptotes. Next. Okay. Find the vertical and horizontal asymptotes for 8x squared plus 5 over 4x squared plus 1. So in this case, we've got to look for vertical asymptotes. That's where the bottom is equal to 0. So we have 4x squared plus 1 equals 0. So I go 4x squared equals negative 1. X squared equals negative 1/4. And then when we try to take the square root of both sides, we get a negative. We can't take the square root of a negative number. So because we can't take the square root of a negative number, that will never equal 0. So there are none. And you can see from the graph, even though it may look like there might be one there, what's really happening on this graph is it's kind of doing this, curving at the y-axis, at the y-axis, and not having a vertical asymptote. For horizontal asymptote, on the other hand, we look at our degrees again. So our degree is 2, our degree is 2. So we take the leading coefficients, which is 8 over 4. So y is equal to 8 over 4, and we reduce that to be 2. So y equals 2 is our horizontal asymptote, and you can see from the graph that that's what it's approaching as you go to infinity and negative infinity. Okay, last one. Okay, find the vertical and horizontal asymptotes for this. Well, in this case, we'll talk about vertical asymptote. We don't have a graph on this one, but that's okay. Set the bottom equal to 0, x plus 4 equals 0, so x equals negative 4. So that's our vertical asymptote, real easy. Horizontal asymptote, we have a degree that's higher on top than it is on the bottom. So if we go back to our rules, degree on top is greater than the degree on the bottom. We have no horizontal asymptote. Okay, so we would say no horizontal asymptote. Okay, now let's talk a little bit about the slant asymptote right now since we have a little bit of time. When you find a slant asymptote, as soon as you know there's no horizontal asymptote on a rational function, you can rest assured there's going to be a slant asymptote. And this is how you find them. It's your favorite thing. Not really. You really hate this. But what you do is you long divide. And I'm going to do this very quickly. So we long divide and we go x goes into x squared, x times. Okay, so x times x is x squared. 4 times x is 4x. Bring these down. Negative x minus a negative 4x is going to be 3x minus 6. X goes into 3x 3 times. Okay, this is not working, so we're going to do... So we have x plus 3 on the top there. It just doesn't want to write. There we go. Okay, so then we do x times 3 is 3x. 4 times 3 is 12. So we do negative 6 minus 12 is negative 18. So that's our remainder. Now, so we have this little function here that's minus 18 over x plus 4. Now, this is the easy part. So you did your long division. Your slant asymptote. Think about slant asymptote. Slant asymptote, we're talking about like, there's my, slant. Okay, or this, there's my slant. We just put it with a dotted line instead of a solid line. So how do we know what that line is going to be? Really easy. Your slant asymptote is going to be the equation of the non-remainder portion. So our slant asymptote here would be y equals x plus 3, and it would just be a dotted line. And then the graph would obviously be approaching that dotted line on both sides of it. Okay, so we'll do a little bit more of this in class as needed, but I wanted to make sure that I pointed that out to you of what happens when you don't have a horizontal asymptote. Kind of an important thing. Moving on, it is a pre-calculus term, pre-calculus topic. It was not covered in Algebra 2. It's not that hard as long as you know how to long divide. So, all right, so that's all I have for you. I will see you in class. Have a good night, day, whatever.